Okay, folks, I guess I'm going to get going. Hopefully, you can hear me. Slightly different setup tonight, so I hope we haven't screwed anything up. Once again, I, apologize for the last couple of weeks. It's been interesting, to say the least. Kind of a cross between a Monty Python show and Keystone Cops, I guess, in that after I had this killer cold, thought I was about to get completely over that. Then it kind of turned into a little bit of a bronchial infection. So had one of those nice little intense, 3 or 4 day antibiotic things. And then felt like over the weekend, Saturday and all, I was kind of getting past that, feeling pretty good. Sitting on my front porch, and the mailman kind of snuck up on me. My dog went running for the mailman. I went running for my dog, and not a good move. Went down on my backside and with my ribs into the edge of a wicker couch there. So I've got 2 cracked ribs, and so if I'm a little short-winded, or if it seems like I'm breathing heavily, it's just because I'm all strapped up, because I know they don't do that as much anymore, but it's a little, getting over the cold and all, it's a little painful to cough. So we're doing the strapping thing so the cough won't be all that bad. So if I happen to start coughing, I'll try to kill the mic, so at least you won't hear me gasping. You'll just kind of see the contorted looks on my faces. But I think I'm okay. I'm back. I've had broken ribs before, and it just hurts like the devil for a month or two, and then you wake up one morning and it's all gone, goes away. So well, hopefully that'll be the way this does too. So anyway, wonderful last 2 or 3 weeks, and as my mother used to say, bad things come in threes. Well, I've had 3 or 4, so I think I'm probably past most of that stuff now. So anyhow, there are. I'm kind of going back through the As You Learn page and opening up new pieces, and I'm also adjusting due dates, due schedules, and things like that to back everything off. 10 days or 2 weeks. I figure that we'll be still have plenty of time to get all the things in that need to happen. Just won't be able to maybe add a few little enhancement pieces at the end, or maybe I'll just plug those up as enhancements that you can access if you want to or not. And so there were 2 primary things I wanted to talk about tonight, or spend time with tonight. And one of them is the notion of the modern scientific method and kind of the logic behind that methodology, and how that leads us into the logic behind statistical analysis, and lay out a little bit more detailed case for how we handle statistical analysis, and at the same time kind of introduce you to t-tests and z-scores and things like that we'll be kind of playing with as we go forward. So hopefully we'll be able to kind of encapsulate that into a couple of sessions, 2 different recordings. One of them will be on the modern scientific method, and the second one will be on the hypothesis testing and error and nature of error and types of errors and things like that. We're not scheduled to meet next week, and as it turns out, I couldn't do that anyhow. We'll meet the following week, but next week I will be producing some. I've actually got into the video production stuff now, so I can produce a couple of videos and fill in some kind of gaps and holes there as we move along to the next piece. Plus the first quote unquote little evaluation experience will be due in 2 weeks. And it's fairly straightforward, and you know, the kind of the examples that we'll either talk about tonight or I'll talk about on video will kind of lead you right into that, so it shouldn't be an issue. Now, you should know how I handle these evaluation things. After a due date, I'll go through and I'll post up a answer sheet, which will have you know, all the answers and the logic used to get those answers. At the same time, I'll kind of go through your papers and kind of get a read of you know, what you may have problems with or what you may not have problems with. Offer some suggestions and feedback. There is not a grade per se, you know, because it is we are in a kind of a mastery model here, and so the key is dealing with the feedback, and the next time you encounter those same things, not making similar mistakes. So you'll receive credit for submitting it, and then we'll kind of work through the mistakes and figure out what we can do there. Sorry, lots of fluids, keep from coughing. Okay. Questions or thoughts about that? I'll talk about it a little bit more later, toward the end of the sessions tonight. Okay. As I know I've mentioned before, but I'll just kind of reiterate it. The whole notion of quantitative analysis, quantitative inquiry, i.e. statistical analysis, came about as a result of the development of what was known in the mid-late 19th century as the modern scientific method. And that modern scientific method was the way in which science became more streamlined, became faster. We were able to arrive at certain conclusions and arrive at outcomes from evidence based on small samples and based upon in a fairly compact period of time. And so it speeded up the whole process of scientific inquiry and development of science. Had some problems, you know, and we'll kind of point one of those out when we talk about the modern scientific method here in a minute. But it had some underlying precursors too. Two things that the modern scientific method was built on was the notion of normal distribution and the notion of random selection. Now, there are different kinds of random. Random selection refers to each individual in an experimental setting having an equal chance of being selected either into the experimental group or the control group, or into either group or any group. And so there's no bias in terms of who might get selected into what group. Very often we have not random selection, but we have what's called random assignment. And random assignment occurs when pre-existing groups are assigned randomly to either be the experimental group or the control group. Now, the problem with that, and it's not being truly random, is because those groups are not comprised in a random manner. I'm recently working on working with a dissertation that defends here in a couple of 2 or 3 weeks. That's looking at non-random assignment of students into classes and whether that creates a bias for the evaluation of teachers. And one of the things that the literature tells you very quickly is that, you know, principals and people that sort of build classes in schools and all don't do that in a random way. There are all kinds of factors that play in, and so you end up with you know, biased subsets of a larger population. So if you just do random assignment, then it's not truly random. So anyhow, the two precursors or normal distribution, and random selection. Okay. Let me see if I can get this to pop up. Playing with a new slight piece of technology here tonight. I always find it, I tried working with whiteboards and things like that online, and those don't work real well, so I decided to go with a doc cam, which seems to work pretty well. And I'm actually using an iPad to provide the images for the doc cam. So I'm trying to get full use of all my technology that I have available here. The basic premise of the modern scientific method is that you would have a population that you drew from. Theoretically, it could be up to infinity. It's never infinity, but it would be random. And the measure that you might be trying to look at, let's say we're looking to see whether some difference in treatments impacts IQs. And so we would have a population that is, we're assuming is fairly random on IQ. There's no reason why it should be biased on IQ. We know that, and so you have this sort of normal distribution here around the mean, and we'll just say the mean IQ is 110. And so the notion of randomness then is that if you select from a random population random groups, those groups will be representative of the population. So if I go in and pick, let me see if I can get rid of some of these lines just real quick. Oh, that's not it. Okay. If I go in and say pick 50 from the population group and place them in one group, pick another 50 at random from the population group, place them in a separate group, subgroup, a sample, we call these samples, then I would expect that the mean values for the IQs in these samples would also be 110, and the distribution would be normal. And so what that would tell us is simply by choosing random samples, I don't really have to measure them or do anything with them. They are going to be equal to each other. And so I have two equal samples. Now, let's say that then I do with the two treatment groups. Let me find myself a tool here. With the two random samples who are equal now, if I do two different treatments, if I do a different treatment for group A than I do group B, and we can call either one of them experimental, either one of them control. Let's just say that they're both, in this instance, they're both an experimental and both a control, because they're the control for each other and the experimental in that we have two separate treatments. And so we have a treatment for group A, a treatment for group B. And then after the treatment occurs, I go back in and I measure the two groups, and I have for group A, mean IQ score of 113. For group B, I have a mean IQ score of 108. And so there's a difference here. There's a difference of 5 points. Well, the question I have to ask is, this difference of 5 points, is that within the range of random error? Or is there something systemic there that's related to the treatment. And so the logic is or excuse me, the hypothesis that we're actually testing is, does a difference in treatment have an impact on IQ scores? And so that's the very most straightforward and simplest logic for the modern scientific method. Now, this modern scientific method bore great fruit, but what it was missing was some way of knowing whether that error was the random error that we expect to see in all groups, or is it also composed of some systemic error? And so the only way to know that is we had to figure out a way of answering that question. So any questions? Okay. Find the second piece here. So we're back asking the question that we brought up a few weeks ago about the nature of error. We know that this difference of 5 points could be a real just random difference, or it could be a systemic difference brought about by some bias, and the most obvious bias in this case would be placement into groups. But we don't know which is which. So the sort of the challenge to the methods folks and the statisticians of the time was to figure out, okay, how do we get at that, answering that question? How do we get at whether it's a real systemic error brought about by some structural element, or whether it's a random error that we could expect to see, pretty much on a random basis. And so the question is that question. And that's the whole point in developing statistical analysis. Now, in in looking at our different outcomes, we have two possible outcomes that we could come to. We could assume that in reality, it is true to say that there is a connection. And if in measuring it, we find that to be true, and we find that it is there is systemic error that we can relate to some factor, then we're okay. But what if in our analysis, because there is always error in everything, including analysis, what if we find that what we think is true by measurement is actually false in reality? In other words, there is no connection, but we have discovered what we think is connection. That's called a type 1 or a false positive error. Now, the obvious inverse to that is that reality could be that it's false, that there is no connection. And we find that to be true when we do the measurement, but we're incorrect. There really is a connection that we didn't find because either our instrumentation wasn't sharp enough or our analysis wasn't good enough. That's called a type 2 or false negative. Type 1 is a false positive, type 2 is a false negative. And what we mean by positive is that there is a significant relationship between the two variables, or a significant difference between the two groups. And so we have two possible scenarios, a false positive or a false negative. Now, the logical issue with this, and the issue that we run into most often when we're trying to look at these things and trying to figure out what we've got confronting us or what we have staring us in the face, is that we really can't know if there's a false negative because we can't find what we don't know. We can establish whether it's a false positive because if we run a similar experiment and we we end up with different results, then that's probably telling us maybe we need to go back and revisit that we might have a false positive. And so we're always testing for false positives. Always testing for false positives. We're never testing for false negatives because we just, we can't know those things. We can't know what we don't know. We can't see what we're not looking for. And so we're always testing, always looking to see if we have a false positive. Any questions? Any okay. So let's look at the nature of hypothesis testing. In fact, let me get back to the doc cam. if we ask the question, well, we asked the question we just did, we asked that as a research question. Is treatment related to IQ? There are two possible outcomes, and so there are two possible hypotheses. We always test the negative. So our HO, or our negative hypothesis, is that the treatment is not related to IQ. That's our what we call our negative hypothesis, or negative hypothesis, is that treatment is not related to IQ. Why do we ask it in that way? Because we want to make it difficult. This is where we're testing, trying not to allow false positives. We want to make it difficult for the for us to find a false positive. And so we want to set a high bar. We want to set a high standard. We also have an alternative hypothesis. H1 in this case. And the alternative hypothesis is that treatment is related to IQ. Now, we can't test that one. And so we have to test the negative hypothesis, or the null hypothesis, to use the research term. And so we have treatment is our independent variable, and IQ is our dependent variable. And so what we're basically testing is that the independent variable is not related to outcomes on the dependent variable. That's what we're actually testing. And so how do we know? How do we do that? That's where the statistical pieces come into play, and we'll kind of get to those in just a bit. But what we actually do is we do our experiment. If you think about that graphic we had earlier, starting with a hypothesis leads us to a prediction, which leads us to an experimental model or observation, which leads us to analysis, which leads us back to hypothesis. But what actually happens is that our prediction is based upon the negative hypothesis. And so we're actually setting an experiment up to test as to whether the negative hypothesis is true or not. Now, we'll have two outcomes. We'll have two outcomes. And the two outcomes or that we will accept the null, or conversely, we'll reject the null. Well, once again, because rejecting the null is related to a type 2 error, we can't know that. And so we can only test whether we can accept the null. Now, if we accept the null, that means because we are testing the null hypothesis, the negative outcome, that means there is no relationship. And so our analysis tells us that there is no relationship, there's nothing to look at here. Our changes to our hypothesis will be reflected in the fact that there wasn't anything going on there. If we fail to accept the null, then by default, we reject the null, which means that our alternative hypothesis is true. And so hypothesis testing is all about figuring out how we know whether there is or what's the level of possibility for a type 1 error, a false positive. And we test that at what's called a p-value. And that p-value we test at is less than 0.05 or less than 5%. So we want it always to be less than a 5% chance, that we could have a false positive. And if we say there is less than a 5% chance, and that's all stats does, it gives us a probability or a chance of an outcome. If we say there is less than a 5% chance, then by default, we have rejected the null and accepted the alternative hypothesis. And we call that significance. If we reject the null, we call that a significant outcome. Okay, there's a fair amount of stuff to unpack there. And so do you have questions as to any of that, any of the sort of the logic of hypothesis testing? Okay, I'm going to turn off the video. Simply want to keep these two pieces separate, so I'm going to turn off the video, take a quick little break, a 5-minute break or so. I'll be right back, and I'll start the second part of the video, or the second video that has to do with the nature of the statistical logic that we build to do hypothesis testing. And we'll base it first around individual scores and what are called standard scores, but then we'll move quickly into looking at means and differences between means and things like that. So take a 5-minute job. I've got 6:36. I'll be back at 6:45. I guess a 9-minute job. So I'll see you at 6:45.